Hello, these are the Exam 2 review slides for spring 2018. With that, so we're going to go ahead and go through these, right? So one thing I do note that there aren't going to be any curved error mechanisms. I know we've talked about them, we've dealt with them with the homework set, stuff like that. So I'm just getting you guys ready because they will be on the next exam, and they're one of the things that students struggle with. But for this test, there won't be. So kicking off for the for free answer part, right? So we are going to be naming molecules, right? So alkanes, alkenes, alkynes, the cyclics, haloalkanes, and alcohols. You won't necessarily get all of these because we only have 50 minutes for the test, but you won't need to study all of them because you don't know what's coming other than these. At the end of the slide deck, there are there are things you can also check out the chapter 3 review slides for that. Otherwise, this review is going to take hours. Look at that. So do look over these. So now you will get a couple that are going to be drawing the molecule from the name. Okay, this is the only time you're going to see this. But I did want to at least practice this a little bit. Okay, the best way to do this is to actually start with the main chain. Okay, so you're going to come in here. So you have cyclo, you have a hexane. So a hexane is 6. The cyclo means it's cyclic. Right? So go ahead and put that there. You can go put in your dots. Always makes it a little easier. So let's go. Right? So we have a 2-propyl group. Right. So remember, this is 3 carbons long. Right? That's what makes it a propyl group. But it's connecting to the main chain. So assuming that's the main chain, it's connecting through carbon 2. Right? So for that of the propyl group. Right. So 1, 2, 3. Right. That makes it a propyl. But it's connecting through carbon 2. So this can also be called an isopropyl group. I don't care which, like when you're doing the naming, I don't care which one you use, but you have to be careful with the alphabetical. So, okay, and then there's also a methyl group, right, hanging out at 1. This one just so happens to be hanging out at carbon 2, and then we've got a bromo group hanging out at carbon 4. Okay, so we could start these anywhere in this case. So let's say this is carbon 1, right? 2, 3, 4, 5, 6. That's why drawing them from the name, it's nice because you can do the numbering where you need, wherever you want to. So at carbon 1, right, we have a methyl group. That. Carbon 4, right, we have a bromine. And then carbon 2, we have this 2-propyl group or isopropyl group. Like this. Okay, so there you go. You can, I've done a mixture of skeletal structure and condensed structure. You can do that. That's fine. If you wanted to do the straight skeletal structure, that's fine too. So CH3, right? It would look like this. I don't care. You can do whatever you need to. Okay, so there you go. Now, as far as cis and trans for cyclic alkanes, right? It's going to say something like, "Is this molecule, are the methyl groups in the cis or trans configuration?" Right. So remember with cis, right, they're either both going to be up or they're both going to be down. Right? For trans, it's going to be 1 up, 1 down. Okay. It doesn't have to do anything with axial or equatorial, although you can use that to tell which one if it's up or down. Okay. So for the cyclopentanes, it's pretty easy, right? Because these are pointing down away from the ring, right? So they're both pointing down, so this is going to be cis. Okay. So for here, right, remember each one, you need an axial, equatorial, you need an up and down in each position. So here the bonds are pointed down, so that means this is the axial's here, and that means the equatorial's there. So this is equatorial, this is axial. More importantly, this is up, that's down. Same thing here. The bonds are pointed up, right? So again, this is axial. That means there's an equatorial over here. More importantly, for the cis-trans, that means this is up, that's down. Okay, so we're comparing this down to this up, so it's trans. It doesn't have, right? So they're both axial, but it's still trans because it's the up-down that makes the difference. So as far as the Newman projection goes, draw the Newman projection of propane in the lowest energy state. Okay? So let's say we're going to look through this bond here. I'll tell you which bond you need to look down, but this one it doesn't really matter. So this is going to be carbon 1, that's going to be carbon 2. So in the front, right, we have this. It's got, say, 3 hydrogens hanging off of it. Now, for it to be at the lowest energy state, right, we're going to have this be in the anti-configuration, right? It's going to be staggered, and it's going to need to be anti. Okay? So in this case, we can do it, say, put this off of carbon 2, which is the one behind this front carbon, right? There's 2 hydrogens, right? There's 2 hydrogens and a methyl group hanging off of there. And so there you go. You could either have, in this particular case, you could put it either way here. So this is the lowest. If I asked you for the highest, right, so the highest, you're going to do 2 things. One, it needs to be eclipsed, and you want the largest things largest together. So on the front carbon, it'd be a hydrogen, and the back carbon, it would be this methyl group. So the highest, if I asked you about this, would be an H, and it's like CH3. It doesn't really matter which H you go on, right? H, like that. So this would be the highest if I had asked you about that. But this one I asked you for the lowest, so it needs to be staggered. For the degree of unsaturation, I'm going to give you this. I'm just going to give you that, right? So I'm not going to give you the formula, but or the key. But remember, this is the number of carbons. This is the total number of nitrogens. This is the total number of halides. So it's fluorines plus chlorines plus bromines plus iodines, right? That's this. Okay, and then the total number of hydrogens. Sorry, I got a shelf here that's ready to fall. Back to chemistry. Okay, so DOU. So it's the degree of unsaturation or the index of hydrogen deficiency. So it's 2 times the number of carbons, in this case it's 8, okay, plus 2, that's a constant, you have to have that in there, plus the number of nitrogens, here it's 1, minus the number of halides, so it's all of those combined. So in this case it's 1, and then the number of hydrogens, minus the number of hydrogens, okay, all divided by 2. Notice even though the oxygen's in here, it's not part of the equation, it does not matter. Okay, so here it's 10, 12, 13, so it would be 13 minus 9, which is 2. So this ends up being 4 halves, which ends up being 2. So it has either, it's got either has 2 pi bonds, a pi bond, and a ring, or 2 rings in it. So there you go. So circle the molecule in each pair that has the most acidic. Okay, so there's 3 ways. So there's a progression chart that you need to go down. The first one being that, look for the most acidic hydrogen. Acidic hydrogen bond, H bond. Maybe instead of hydrogen bond, maybe say H atom bond. What you want is the atom closest to iodine on the periodic table. Iodine. Okay. If that's a tie, then you say, okay, you're looking for an adjacent pi bond. Oop. Pi bond. Okay, so you're thinking things like carbon-carbon double bond. CO bond, right? CN bond, etc. Okay. If that's still a tie, then you go to the most electronegative. Most and or closest electronegative atom nearby. Okay, and remember this is the closest to fluorine on the periodic table. Okay, so this one is where students get it, is that they say you have to sort of take a switch. So the most acidic H bond, it's the one closest to iodine. So in here, you would be pH versus NH here. So that, they're different, right? And so this, the phosphorus is closest to iodine on the periodic table, so this is going to win. Now, if you're looking at, say, this versus, this versus, say, this, okay, the most acidic H atom bond, right? So that would be this versus this. That's a tie. So then we go down here. Do either of them have an adjacent pi bond? No, they don't. It's just single bonds. Then you come down here and you say the most or closest electronegative atom nearby. So then it's fluorine versus chlorine. So here, this is more electronegative than this one. Fluorine is more electronegative than chlorine. So this would be the most acidic. Okay, so after this first step, then you want to be closer to chlorine. It's just the atom here. You can sort of think about it if, right, if you think about just the mineral acids here, HI. Fluorine is actually a fairly weak acid, but HCl is really strong. So the trend continues. HBr is a little stronger. HI is actually the strongest of the four. So that's the trend, right? Because that's where the acidic hydrogen is. It has to deal with the fact that the bromine is much bigger. There's a lot of core electrons shielding its nucleus, so this bond just simply can't be held very tightly. Here, it's got a very small core electron set, and so it can hold on to this hydrogen. When you get down here, then you're just going to the regular electronegative, right? Fluorine's a lot more electronegative than chlorine, so this is going to be the most acidic bond because this is going to be pulling electron density this way stronger, and weakening that bond more than this one here. So just be careful. That's what these trends are here, right? So furthest from the further right on the periodic table, so right here. So you want to go like this and like this on the periodic table. Okay. So for atoms in the periodic same column, so down here, right, you want to get close to iodine. Hybridization does matter. Okay, so this is particularly with carbon-carbon triple bonds versus double bonds versus just regular alkanes. Okay. These are going to be much. This carbon here, it's an sp. The hybridized, so this CH bond is going to be fairly weak relative to other C bonds. Adjacent pi bonds make things a lot stronger, right? There's a reason why this is called a carboxylic acid. Okay, it's because it has an adjacent pi bond next to it. But this one also does as well, but this is carbon oxygen, so this is much more electronegative than this carbon here, so you're going to need that. Plus you get a lot better resonance structures, but that's the point. You have something electronegative right next to here. Okay? So that's going to be, so this would be the most acidic than this, because again, it's got the pi bond in that. Okay? Inductive effects. And so the more electronegative it is, the more likely it is to be acidic. Also, the closer it is. That makes a difference. Last but not least, which one for the reverse? The reaction is going to want to go towards the higher pKa of the either acid or conjugate acid, right? So this is the acid on this part, right, or the conjugate acid. going to want to go to the higher numbered side. So here you're negative 8 versus 16, and so the reaction is going to want to go this way, so it's going to want to go forward. Okay? It doesn't matter what the numbers are. It can go from negative 8 to negative 6, or it can go to 6 to 8. It doesn't matter. It's always going to want to go